On the 1st of June 2026, the calendar marks a long-established operational boundary, the official opening of the Atlantic hurricane season, a 6-month corridor stretching to the 30th of November. For generations, this temporal window has defined the period of tropical cyclone risk across the basin. Yet this year, the calendar presents a profound scale paradox. While the Atlantic formally opens today under predictions of unusual calm, the Eastern Pacific Basin has already been operational for over a fortnight, having commenced on the 15th of May. Across the same hemisphere, under identical solar forcing, two adjacent oceanic basins are displaying thermodynamic trajectories so fundamentally divergent that they appear to exist in entirely different years. One ocean is being systematically suppressed, while the other is being supplied with immense thermal energy and atmospheric instability. This spatial and temporal split is not a statistical anomaly or a matter of chance. It represents a strict architectural redistribution of energy recorded directly in the physical state of the global ocean atmosphere system. On the morning of June 1, 2026, telemetry from the National Hurricane Center documented two distinct low-pressure disturbances actively organizing in the eastern Pacific. The first, situated southwest of the Baja California Peninsula, exhibited favorable thermodynamic conditions, carrying a 40% probability of organizing into a tropical depression within 48 hours and a 90% probability over 7 days. The second disturbance, located further south off Central America and Mexico, registered near zero 2-day odds, but a 30% 7-day probability within an environment expected to grow increasingly hospitable. This Pacific acceleration contrasts sharply with the official seasonal baseline established on May 21, 2026, when NOAA convened at its Aircraft Operations Center in Lakeland, Florida. The joint outlook, synthesized by the Climate Prediction Center, the National Hurricane Center, and the Atlantic Oceanographic and Meteorological Laboratory, delivered a starkly asymmetrical forecast. For the Atlantic, forecasters projected 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes reaching Category 3 or higher with winds exceeding 111 miles per hour. NOAA assigned a 55% probability to a below-normal Atlantic season, a 35% chance of near-normal activity, and only a 10% chance of an above-normal year, backed by a 70% confidence interval. Concurrently, the projection for the Eastern Pacific flipped completely. NOAA forecasted 15 to 22 named storms, 9 to 14 hurricanes, and 5 to 9 major hurricanes, establishing a 70% likelihood of an above-normal season. As National Weather Service Director Ken Graham emphasized, even within a suppressed Atlantic framework, a single landfalling system negates the statistical abstraction of a quiet year. Yet the core analytical question remains. Why does the same planetary engine yield diametrically opposed structural outcomes across adjacent oceanic basins during the exact same seasonal window? The mechanical root of this dual baseline is not situated within the Atlantic itself, nor does it originate within the local architecture of the storms. It stems from a singular thermal shift expanding along the equatorial Pacific. Historically observed 4 centuries ago by South American fishermen as a seasonal ocean warming around Christmas, and named El Nino, this phenomenon represents a primary driver of the global climate machine. In 2026, subsurface ocean telemetry reveals a massive reservoir of anomalous heat gathering beneath the central and eastern equatorial Pacific, setting the stage for a potential super event comparable to the historic benchmarks of 1982, 1997, and 2015. Under baseline conditions, steady trade winds displace warm surface water westward, piling heat near Indonesia and driving cold, nutrient-rich upwelling off South America to maintain the Walker circulation. During an El Niño phase, those trade winds weaken or collapse, allowing accumulated warm surface water to slosh back eastward across the Pacific. This displacement reorganizes the rising branch of the Walker circulation, and alters long-range atmospheric teleconnections across the globe. Yet, predictive models are locked in a sharp internal contradiction regarding the peak amplitude of this event, with advanced European guidance projecting a historic super El Niño, while official diagnostic discussions flag significant coupling uncertainties. How does this single equatorial thermal shift simultaneously construct a suffocating barrier over the Atlantic while handing the Pacific a tank of fuel and a lit match? To comprehend how a localized thermal anomaly on the equator can simultaneously suppress one oceanic basin and supercharge another, we must examine the specific fluid dynamics governing tropical cyclone mechanics. A hurricane is fundamentally a thermodynamic heat engine. It extracts sensible and latent heat from warm ocean waters, typically requiring sea surface temperatures of 80 degrees Fahrenheit or higher, and converts that energy into an organized rotating column via deep atmospheric convection. However, the conversion of surface thermal energy into kinetic storm structure requires a critical atmospheric boundary condition: low vertical wind shear. Vertical wind shear represents the vector difference in wind speed and direction between lower altitudes and upper atmospheric levels around 35,000 feet. When shear is minimal, the upper and lower circulations of a developing cyclone remain vertically aligned, allowing the thermodynamic core to stack, retain latent heat, and intensify explosively. Conversely, high vertical wind shear exerts a destructive mechanical force on the system, laterally displacing the upper-level outflow from the low-level center and physically tearing the tops off developing convective towers before a closed circulation can consolidate. This is where the mechanical physics of El Niño dictates the contrasting fates of the two basins. As equatorial surface waters warm and displace eastward across the central Pacific, the rising branch of the Walker circulation shifts with them. Millions of tons of warm, moist air ascend into the upper troposphere over the central Pacific and discharge eastward toward the Americas and the tropical Atlantic. This high-altitude atmospheric transport sharply increases upper-level westerly winds over the Atlantic main development region, running directly counter to low-level easterly trade winds. The resulting high wind shear acts as an environmental barrier across the Atlantic basin. Compounding this structural suppression, the altered planetary circulation forces sinking air over the Atlantic basin. Descents of dry, warming air stabilize the mid-tropospheric layers, suppressing moist updrafts and starving potential storms of buoyancy. The Atlantic thus faces a dual mechanical constraint: severe wind shear physically disassembling convective cores, and large-scale atmospheric subsidence drying out the thermodynamic fuel supply. This structural barrier forms the physical basis for NOAA's Quiet Atlantic forecast and its 55% probability of a below-normal season. In the eastern Pacific, the exact same atmospheric shift operates in reverse. Because the basin sits directly adjacent to the expanding thermal warm pool, its surface waters receive an immediate increase in ocean heat content. Simultaneously, the eastward migration of deep convection relaxes upper-level wind shear across the eastern and central Pacific. The atmosphere shifts into vertical alignment, creating uniform wind profiles and lower environmental resistance. The Pacific is thus granted a dual advantage: elevated ocean heat content for fuel and minimal shear for structural organization. However, a suppressed seasonal forecast in the Atlantic introduces a dangerous cognitive trap: the baseline assumption that a below-normal seasonal projection equates to regional safety. A seasonal forecast provides an aggregate metric of basin-wide activity over 6 months. It contains zero spatial information regarding cyclone trajectories or localized landfall vectors. Historically, suppressed Atlantic seasons under El Niño conditions have produced high-impact disasters. In 1991, an El Niño-influenced year with suppressed overall counts still generated Hurricane Bob, which struck New England as a major storm. Furthermore, antecedent drought conditions across regions like the southeastern United States mean that hardened, dry soils shed extreme rainfall rather than absorbing it, compounding urban runoff and catastrophic flooding risks from a single landfalling system. A quiet seasonal average is a statistical abstraction. The single storm that makes landfall is an absolute physical reality. While the Atlantic operates under atmospheric suppression, the Pacific Basin faces a structural setup engineered for maximum kinetic energy. NOAA's forecast of 15 to 22 named storms, 9 to 14 hurricanes, and 5 to 9 major hurricanes in the eastern Pacific reflects an environment where every thermodynamic boundary condition has been optimized. Yet the true systemic risk of an active Pacific season is defined by vector expansion, the physical pathways through which tropical cyclones alter hazards far beyond their genesis zones. Historically, the vast majority of eastern Pacific systems track west-northwest into open ocean waters, decaying over cooler SST gradients without impacting terrestrial infrastructure. Under strong El Niño conditions, however, this baseline trajectory shifts along two primary operational vectors. The first vector extends westward toward the Central Pacific and the Hawaiian archipelago. The Central Pacific season, which also opens on the 1st of June, carries a 70% probability of above-normal activity, with 5 to 13 tropical systems projected. In a thermal regime dominated by El Niño, tropical cyclones maintain structural integrity further west, increasing the frequency of near-miss events. As demonstrated by Hurricane Eva in 1982, a system passing within 25 miles of the coast without making technical landfall can still generate destructive wind fields and storm surges capable of crippling island infrastructure. The second operational vector directs deep tropical moisture northeastward into the arid regions of the southwestern United States. Decaying tropical depressions and atmospheric moisture plumes originating in the eastern Pacific are drawn into continental circulation patterns, transporting vast quantities of precipitable water into Southern California, Arizona, and Nevada. Desert topographies, characterized by low infiltration capacities and unengineered drainage basins, are exceptionally vulnerable to rapid surface runoff, turning minor tropical remnants into severe urban flood events far inland from hurricane zones. To evaluate the upper boundary of this Pacific setup, we must analyze the historical benchmarks established by previous Super El Niño events in 1982, 1997, and 2015. In 1997, the Eastern Pacific generated Hurricane Linda, which achieved a central pressure of 912 millibars and sustained winds of 185 miles per hour, alongside Hurricane Nora, which delivered inland flooding across the Colorado River Valley. That same year, the Western Pacific recorded 10 Category 5 super typhoons, including the simultaneous occurrence of super typhoons Joan and Yvonne. The 2015 season established an even more extreme benchmark, producing 31 tropical depressions, 16 hurricanes, and 11 major hurricanes across the eastern and central Pacific. That season culminated in Hurricane Patricia, which intensified over sea surface temperatures of 87 to 88 degrees Fahrenheit to achieve sustained winds of 215 miles per hour and a central pressure of 872 millibars, the most intense tropical cyclone ever recorded in the Western Hemisphere. The physical lesson of Patricia is clear. When subsurface ocean heat content reaches extreme levels, atmospheric convection can undergo explosive intensification that exceeds traditional predictive baselines. Evaluating the 2026 hurricane season requires navigating a profound scientific tension between high-amplitude model projections and official diagnostic caution. On one side of the modeling landscape, long-range guidance from the European Forecasting Center and high-resolution climate models project the incoming El Niño to comfortably clear the threshold for a super event, reaching values comparable to 1982, 1997, and 2015. Subsurface ocean heat content, measured in early 2026, ran at more than twice the levels recorded at the same point prior to the recent El Niño, indicating that the thermal reservoir beneath the equatorial surface is extraordinarily loaded. Conversely, NOAA diagnostic discussions maintain a deliberate analytical restraint, emphasizing that peak strength confidence remains limited, with no single intensity category holding more than a 1 in 3 probability. This caution stems from two fundamental structural factors: the spring predictability barrier and an altered global climate baseline. Predictions formulated during the spring window inherit significant signal noise before atmospheric-oceanic coupling fully locks during the summer months. Furthermore, global sea surface temperatures in early 2026 reflect baseline warming, meaning this El Niño is unfolding within an unprecedented thermal background, where historical analogs may no longer offer precise physical templates. This structural uncertainty splits the potential evolution of the 2026 season into three distinct probabilistic trajectories. The first trajectory is the record breaker. Deep ocean-atmosphere coupling locks in through summer, triggering a historic super El Niño that maximizes Pacific intensity while keeping the Atlantic severely suppressed. The second trajectory represents a strong but sub-historic event, where El Niño achieves solid intensity, maintaining the classic basin split without breaking historical intensity records. The third trajectory is the under-delivering scenario. If ocean-atmosphere coupling remains weak, atmospheric shear over the Atlantic breaks down prematurely, exposing vulnerable coastlines to an unexpected surge in late-season activity. The exact failure mode that turns seasonal quiet forecasts into catastrophic human surprises. To monitor which path the 2026 season selects in real time, 6 empirical telemetry signals must be tracked. First, monitor the sea surface temperature anomaly in the Central Pacific ONI region as it crosses the 1.5 degrees Celsius threshold toward 2 degrees. Second, observe whether atmospheric coupling materializes through sustained tradewind collapse and the eastward shift of deep convective towers. Third, track Atlantic activity during its climatological peak from August through October to verify whether shear suppression holds. Fourth, monitor the Eastern Pacific for rapid intensification events and major hurricane counts. Fifth, watch Central Pacific genesis rates and tracks approaching Hawaii. Sixth, track tropical moisture transport into the arid southwestern United States. On this first day of June 2026, as two systems turn in the Pacific while the Atlantic opens its 6-month operational window, the physical architecture of the global climate machine is already active. The observational models are deployed. Uncrewed weather drones are feeding real-time internal cyclone data into forecast systems, and the planetary engine is running. The task now is not to guess the final outcome, but to track the physical signals as the season unfolds across two oceans. As the 6-month operational window of the 2026 hurricane season progresses, the fundamental lesson of this planetary-scale system becomes starkly evident. Nature operates strictly through the hard limits of fluid dynamics and thermodynamic energy budgets, completely indifferent to human calendar boundaries or seasonal expectations. The split behavior of the Atlantic and Pacific basins demonstrates that our global weather architecture is a deeply integrated, highly sensitive machine. A shift of a few degrees in sea surface temperatures along a narrow strip of the equatorial Pacific is sufficient to re-engineer global wind shear patterns, relocate atmospheric convective cells, and completely invert the disaster exposure risks for tens of millions of people across 2 ocean basins. This systemic reality thoroughly deconstructs the common, dangerous misconception that a quiet seasonal forecast implies safety or reduced vigilance. The statistical abstractions of seasonal totals, whether predicting 8 named storms or 22, offer zero guarantee against localized destruction. The mechanical threshold required to turn a quiet year into a human disaster is exactly 1 storm finding a coastal trajectory. As demonstrated by historical precedents like Hurricane Bob during the suppressed 1991 Atlantic season, or Hurricane Eva passing near Hawaii in 1982, the physics of atmospheric circulation do not require an active basin-wide outbreak to inflict catastrophic infrastructure failure. Furthermore, the ongoing evolution of the 2026 season highlights the structural boundaries of our predictive capability. While modern sensor networks, next-generation satellite telemetry, and uncrewed weather aircraft penetrating storm cores have increased forecast model precision, yielding up to a 10% improvement in intensity forecasting, the system itself presents inherent mathematical limits. The spring predictability barrier, combined with an elevated planetary baseline where sea surface heat content continually exceeds historical norms, forces atmospheric scientists to operate within an evolving statistical paradigm. Models can outline probabilities, project shear vectors, and measure subsurface thermal banks, but the precise coupling between ocean and atmosphere remains a real-time fluid mechanical experiment. Ultimately, the 2026 season exposes the rigid physical constraints under which human communities exist alongside macro-ecological systems. Whether facing the suppressed Atlantic, where hardened drought soils amplify landfalling flood risks, or the supercharged Pacific, where deep ocean heat reserves stand ready to fuel explosive, rapid intensification, the imperative remains uniform. Systemic preparation, evaluating evacuation routes, reinforcing infrastructure, and maintaining operational readiness during periods of apparent calm is the only rational, pragmatic response to a geophysical machine whose internal mechanics are fully active, whose limits are strictly physical, and whose trajectory will continue to unfold according to the precise laws of fluid motion.